Hello and welcome to the BS Academy. So recently IIT Bombay has changed their syllabus a little bit to the each branches. So according to the new syllabus, we have made these charts in our best possible ways, and these charts basically give you an idea how to prepare your own charts, because ultimately you have to make your own charts of every subject, and after that you will get that confidence. So basically these charts will give you the ideas and perfect information after referring all the reference books. So let's begin with the first subject of GATE Mechanical 2021, thermodynamics. So basically third chart of thermodynamics includes total 12 cycles of the thermodynamics. So let's see one by one. The first cycle is Carnot vapor cycle, second one is Rankine cycle, third one is Breton cycle, fourth one is air refrigeration cycle, which is also known as Bell-Coleman cycle, then fifth one is Erection cycle, sixth one is Stirling cycle, then number 7 is ideal refrigeration cycle, then 8th one is VCRS, 9th one is VARS, then 10th number is Otto cycle, number 11 is air standard dual cycle, and number 12 is air standard dual cycle. So these are the total 12 cycles which is considered in this video in one chart only. Before moving towards the Carnot vapor cycle, let's see some history about the thermodynamic IC engines. So it was all started from the 17th century. So in 1680, Christian Huygens first ever developed the IC engine, which was operated by the gunpowder. After that, the first practical engine was invented by J.J. Linear in 1860, and he gave one equation of efficiency, that eta is equal to 1 minus r into rp raised to 1 by gamma minus 1 upon rp minus 1. So efficiency of that engine was 4%. Then in 1876, Nicholas Otto developed one SI engine which is of 4-stroke. Then in 1878, D. Clark developed one 2-stroke IC engine. Then in 1882, Atkinson developed an engine. This is some history about IC engine. So now, overall, if we think about the thermodynamic cycles, it includes 3 types. First one is power cycle, then second one is refrigeration cycle, and third one is IC engine. So basically power cycle includes vapor power cycle and gas power cycle. Then refrigeration cycle includes vapor refrigeration cycles and gas refrigeration cycles. Then IC engine includes Otto cycle, diesel cycle and dual cycle. So in general, for all the cycles, we have noted down the PV diagram and TS diagram and also the efficiency equations of the respective cycles. So let's see for the Carnot vapor cycle. There are 2 diagrams here. First one is PV diagram and second one is TS diagram. You can take a screenshot if you want and then note down the diagram. And the efficiency equation for the Carnot vapor cycle is eta C is equal to W upon Qn is equal to Th minus TL upon Th. After that, the process on which the cycle work is process 1 to 2 is isentropic compression, which is adiabatic process. Then process 2 to 3 is isothermal expansion. Then 3 to 4 is isentropic expansion, and 4 to 1 is isothermal compression. In process 2 to 3, heat is added, and in process 4 to 1, heat is rejected. That the efficiency equation of Carnot cycle is eta C is equal to 1 minus TL upon TH is also equal to 1 minus T2 upon T1. Here T1 greater than T2. So then the second and the most important cycle is Rankine cycle. So here in the diagram you can see that the first one is pump, then boiler, then third one is turbine, and fourth one is condenser. So main 3 problems are there in the Carnot cycle which are solved by Rankine cycle. So first problem is design and control of partial condenser is very difficult. Then second problem is device increases the pressure of L plus V, means liquid plus vapor region is difficult. Then third one is during process 3 to 4 quality of steam decreases cause wear and tear in the turbine. So all the three problems are solved by the Rankine cycle. In the Rankine cycle, process 1 to 2 is reversible adiabatic isentropic compression. Then process 2 to 3 is isobaric heat input. Then 3 to 4 is isentropic expansion, and process 4 to 1 is isobaric heat rejection. And efficiency equation for the Rankine cycle is eta is equal to Wt minus Wp upon S3 minus H2. Here Qin is equal to S3 minus H2 and Qr is equal to H4 minus H1. And one more equation which is mostly useful in the examination is ms dot into H4 minus H1 is equal to m dot W into 4.18 into T2 minus T1. So here m dot S is equal to for steam and m dot W for water. So after that, the comparison between the Carnot and Rankine cycle. The first one is the efficiency, which is higher in the Carnot cycle, thermal efficiency, which is also higher in the Carnot cycle, then mean average temperature line, which is also higher in the Carnot cycle, then fourth one is bake work ratio, which is also higher in the Carnot cycle, and fifth one is specific steam consumption, which is lower in the Carnot cycle. So in the Rankine cycle, there are main 2 points which is higher. The first one is the work ratio and second one is the specific steam consumption. So from the less steam we can get the more work in the Rankine cycle. So after that, there are main 5 points are there which affects the efficiency. So first one is by increasing the boiler pressure, efficiency will increase. Then the decreasing the condenser pressure, efficiency will increase. Then by superheating, efficiency will increase. By reheating, efficiency will maybe increase or decrease. Then fifth one is by regeneration, efficiency will increase. So this is all about the Rankine cycle. Then moving towards the third cycle, which is Brayton cycle. So here the diagram for the Brayton cycle is shown in the figure, and two charts for PV diagram and TS diagram is also there. You can take the screenshot if you want. Then Brayton cycle operates on these 4 processes. For process 1 to 2, there is reversible adiabatic compression. For 2 to 3, constant pressure heat addition. Then 3 to 4, reversible adiabatic expansion. Then 4 to 1 is constant pressure heat rejection. And there are 3 to 4 formulas which is mostly asked in the GATE examination. First one is optimum efficiency. Eta opt is equal to 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, where T1 less than T2. Then equation for the T2 and T3 and T4. So T2 by T1 is equal to T3 by T4 is equal to Rp raised to gamma minus 1 upon gamma, and eta opt is also equal to 1 minus under root T min by T max. Only air can be used where gamma is equal to 0 to 1.4, and a high gamma value fluid like helium or argon cannot be used for this system. So by increasing the pressure ratio, efficiency will increase, and for increasing the gamma, efficiency will increase. Brayton cycle is mainly used in aircraft applications. Second one is mean temperature of heat addition. TMA is equal to Q in upon S2 minus S1. Eta IR is equal to 1 minus T min by T max into Rp raised to gamma minus 1 upon gamma. Then Brayton cycle with machine efficiency, Rp optimum is equal to eta T into eta C into T max by T min raised to gamma upon 2 into gamma minus 1. So here eta T is equal to W actual by W reversible equal to Cp into T3 minus T4 dash upon Cp into T3 minus T4, and eta C is equal to Cp into T2 minus T1 upon Cp into T2 dash minus T1 is equal to W reversible upon W actual. For open system, in the terms of air fuel ratio, AFR into Cp at T2 plus Cv into eta combination is equal to 1 plus AFR into Cp into T3. For closed system, air fuel ratio is equal to AFR into Cpa into T2 plus Cv into eta combination is equal to AFR into Cpa into T3. After that, the effect of reheating, regeneration and intercooling on the Brayton cycle. The first one is regeneration. By regeneration, efficiency of Brayton cycle will increase. So, first case, excess heat from 4 and 8 to 2. So, effectiveness of the regenerator E is equal to delta T actual upon delta T max is equal to T3 minus T2 upon T5 minus T2. So, efficiency is equal to 1 minus TMR upon TMA is equal to 1 minus Tmin by Tmax. So, efficiency is increased. After that, second one is reheating. In the reheating, expansion is done in 2 or more stages. So efficiency is equal to WTU. So efficiency is equal to WT minus WC upon Qin, and efficiency will decrease. But the slope of regeneration is increased. Here RP is equal to RP high pressure turbine into RP of low pressure turbine. In the intercooling, generally the efficiency will decrease, but maybe it possible that efficiency will later increase. Then fourth one is reheating plus regeneration. So by using both the operation, the efficiency will increase. The fourth one is using the regenerator and reheater at the same time, then efficiency will increase. And the fifth one is using the regenerator plus intercooling at the same time, then efficiency will increase. Here note one point that the efficiency from the use of regenerator and the intercooler is greater than the use of reheater plus regenerator. And the eighth one is use of reheater, regenerator and intercooler, then efficiency is increased. So now the fourth one is air refrigeration cycle, which is also known as Bell-Kalman cycle, or you can say that reverse Brayton cycle. So there is the chart for that cycle, and two diagrams are there, TS and PV diagrams. So for remembering the TS and PV diagrams, you can compare the diagrams of this cycle with the Brayton cycle diagram. Then the COP of refrigerator is equal to 1 upon Rp raised to gamma minus 1 upon gamma minus 1. Then T2 by T1 is equal to T3 upon T4 is equal to Rp raised to gamma minus 1 upon gamma. Then W is equal to MCP T3 minus T4. Then WC equal to MCP T2 minus T1, and W net is equal to WC minus WE. The processes which includes the air refrigeration cycle are 1 to 2 isentropic compression, 2 to 3 pressure is equal to constant, which means isobaric heat rejection. Then 3 to 4 is isentropic expansion, and 4 to 1 is isobaric heat addition. After that, there is one concept of equivalence ratio, which is equal to phi. The phi is equal to F by A of actual upon F by A of stoichiometric. So if phi greater than 1, then rich mixture. If phi is equal to 1, then stoichiometric, and if phi less than 1, then lean mixture is there. So this is all about the fourth cycle, which is air refrigeration cycle. Then coming towards the fifth and sixth cycle, which is Erection cycle and Stirling cycle. There is only two diagrams are there for both. First is the TS diagram for Erection cycle, and the second diagram is for Stirling cycle. So basically Brayton cycle with many intercoolers and many reheaters are known as Erection and Stirling cycles. So in the Erection cycle, two processes are isothermal and two processes are isobaric. In the Stirling cycle, two processes are isothermal and two are isochoric process. And the efficiency of the Erection and Stirling cycle is equal to efficiency of the Carnot cycle. So eta E is equal to eta C is equal to 1 minus T min upon T max. So these are the 6 cycles of thermodynamics. Now moving towards the 7th cycle. So basically ideal refrigeration cycle includes two types. First one is reverse Carnot cycle. The diagram of T versus S is here for the reverse Carnot cycle, and COP of R is equal to desired effect upon work input is equal to RE by Wn is equal to QL upon QH minus QL, which is equal to TL upon TH. is equal to TL upon TH minus TL is equal to RC upon Qin. Then COP of heat pump is equal to HE upon WN is equal to QH upon QH minus QL is equal to TH upon TH minus TL. Then the second one is ideal vapor refrigeration cycle. The TS diagram is also there for that cycle. Then COP of R is equal to TL upon TH minus TL is equal to H1 minus H4 upon H2 minus H1 minus H3 minus H4. This equation is used in the gate examination in 2 to 3 times. Then COP of heat pump is equal to HE upon WN is equal to TH upon TH minus TL is equal to H2 is equal to H2 minus H3 upon H2 minus H3 into TH minus TL upon TH. Then there is one topic of refrigeration. 1 ton of refrigeration is equal to 3.5 kilowatt is equal to 12,000 BTU per hour. After that, definition of the ton of refrigeration. The amount of heat which is to be extracted from the 1 ton of water at 0 degrees Celsius in order to convert it into 1 ton of ice at 0 degrees Celsius in 24 hours. After that, cascade refrigeration system. If the desired storage temperature is very low, then the corresponding energy pressure is very low, and which results into higher pressure ratio. Then the volumetric efficiency will decrease. So for improving the volumetric efficiency, the cascade refrigeration system will be used. So COP of 1 is equal to QL upon W1 and COP of 2 is equal to Q upon W2. Here Q is equal to QL plus W1. So COP of cascade is equal to QL upon W1 plus W2 and COP of cascade is equal to COP of 1 minus COP of 2 upon 1 plus COP of 1 plus COP of 2. So if the diagram shown in figure, so for the diagram shown in figure, if the question will be asked, then you can use this equation directly in the examination for the cascade system. Then coming towards the 8th cycle, which is VCRS, vapor compression refrigeration cycle. So in the VCRS, 4 components are there. First one is the compressor, then evaporator, then throttling valve, and then condenser. So the TS diagram and pH diagram for the VCRS system are there. You can take a screenshot because this is very important cycle for the examination. And the COP of refrigeration is equal to RE upon WN is equal to H1 minus H4 upon H2 minus H1 is also equal to H1 minus H3 upon H2 minus H1. Then COP of heat pump is equal to HE upon WN is equal to H2 minus H3 upon H2 minus H1. After that, cycle number 9 is VARS, which is also known as vapor absorption refrigeration system. So the diagram for that system is here, which includes the evaporator, throttling valve, then condenser, then the generator, then pump, then absorber, and then evaporator. For the VRS system, Q0 equal to Q in plus QG, then Q0 by T0 equal to Q in by T plus QG by TG. Then COP and RE of VRS is very low and very difficult to achieve the low temperature. This cycle is mainly used in solar refrigeration plant. Then COP maximum is equal to QE by QG is equal to TG minus T0 upon TG into TE upon TO minus TE. So just this equation you have to remember from the VRS system. So in the VCRS system, similar to the Breton cycle, the effects of some points are there. First one is decreasing the evaporator pressure. So by decreasing the evaporator pressure, efficiency will decrease. Then second one is condenser pressure increase, then the efficiency will decrease. Then COP of R is also decreased. Then third one is superheating. If COP of refrigerator will increase or decrease, then volumetric efficiency will remain same. Then fourth one is subcooling. So by subcooling, COP of refrigeration will increase and volumetric efficiency will remain same. Then by superheating and subcooling, COP of refrigeration will increase and if volumetric efficiency will remain same. Then the very most important point are there, which is mean effective pressure. Mean effective pressure basically used to compare the performance of two engines of different size. Power is equal to Pm into A into L into N upon 60. Here small n is equal to n for the 2-stroke engine, and here small n is equal to n by 2 for the 4-stroke engine. And power is also equal to W by T. So here one example is also there for that. Then P is equal to Pm into Vs into n upon 60 into 2. That is for 2-stroke engine. And Pm is equal to W net per kg upon V1 minus V2, where R equal to V1 by V2. Now after completing the power cycles and refrigeration cycle, the third one is IC engine, which includes the final 3 cycles are there. So the 10th cycle is Otto cycle. Otto cycle is also known as air standard Otto cycle. So the diagram for the Otto cycle is shown here. So the first diagram is PV diagram and the second diagram is TS diagram. The process on which the Otto cycle runs, the first process is from 1 to 2 isentropic compression, then 2 to 3 isochoric queuing, then 3 to 4 isentropic expansion, then 4 to 1 isochoric heat rejection. And the equation of compression ratio is equal to Vc plus Vs upon Vc, which is equal to volume before compression divided by volume after compression. Then equation for the T1, T2, T3 are T2 by T1 is equal to R raised to gamma minus 1, which is equal to T3 by T4, and T2 by T1 is equal to Pt by P1 raised to gamma minus 1 upon gamma, and T2 by T1 is equal to V1 by V2 raised to gamma minus 1. Then compression ratio, which is for process 1 to 2, then R is equal to Vs plus Vc by Vs, which is equal to V before compression divided by V after compression. So R is equal to V1 by V2 and T3 by T4 is equal to V4 by V3 raised to gamma minus 1. QR is equal to MCV T4 minus T1 and QE is equal to MCV T3 minus T2. Then expansion ratio is equal to RE. RE is equal to V4 by V3, which is also equal to V1 by V2. Then for Otto cycle, V1 is equal to V4 and V3 equal to V2. So RE is equal to R, means expansion ratio is equal to compression ratio, which is equal to V1 by V2 is equal to V4 by V3. For Otto cycle, efficiency is equal to 1 minus 1 upon R raised to gamma minus 1. And also efficiency is equal to 1 minus QR by Q in, which is for SI engine. Here note one point that efficiency of diesel cycle is greater than for Otto, and the pressure ratio for the diesel cycle is also greater than for Otto cycles. Now coming towards the 11th cycle, which is air standard diesel cycle. The PV diagram and TS diagram is there for that cycle. So first equation for process 1 to 2 is T2 by T1 is equal to V1 by V2 raised to gamma minus 1 into R raised to gamma minus 1. Then T3 by T2 is equal to V3 by V2 is equal to cutting ratio, which is equal to RC. Then T3 by T4 is equal to V4 by V3 raised to gamma minus 1 is equal to RE raised to gamma minus 1, which is expansion ratio. And the fourth one is T4 is equal to T1 into RC raised to gamma, and T3 is equal to T1 into R raised to gamma minus 1 into RC. For diesel cycle, RE is equal to R by RC. Then RE is equal to V4 by V3, which is equal to V1 by V3. Then Qin is equal to MCV T3 minus T2, and QR is equal to MCV T4 minus T1. For ideal cycle CI engine, eta is equal to 1 minus 1 upon gamma into T4 minus T1 upon T3 minus T2, and efficiency is equal to 1 minus 1 upon gamma into R raised to gamma minus 1 into RC raised to gamma minus 1 upon RC minus 1. This is the equation for the air standard diesel cycle. By increasing the pressure ratio, efficiency will increase. By increasing the gamma, efficiency will increase, and by increasing the cutting ratio, efficiency will decrease for the air standard diesel cycle. Then the comparison between the Otto and diesel cycle. For case 1, for same compression ratio, then eta greater than eta dual greater than eta diesel, and efficiency is equal to 1 minus QR upon Qin. Then second one is for same pressure ratio and same heat rejection, then eta greater than eta dual greater than eta diesel, and third case is for same maximum temperature and same heat rejection, eta diesel greater than eta dual greater than eta Otto. These are the three cases which you have to remember and most MP cases. Then there is one topic of engine performance parameters. It includes first one is power, which is equal to rate of doing work, P is equal to W by T is equal to F into E is equal to T into theta. Then second one is brake power, which is equal to BP is equal to 2 pi NT by 60. Third one is the indicated power, IP is equal to FP by plus BP. Then fourth one is indicated specific fuel consumption, ISFC, which is equal to m dot F upon I into P, means ICFC is equal to m dot F upon indicated power, where Vs is equal to pi by 4 d square into L, where L equal to 2R, which is equal to swept volume. Then indicated thermal efficiency, eta IT is equal to IP upon the Qin, and brake thermal efficiency, eta BT is equal to BP upon Qin. Then mechanical efficiency, eta M is equal to BP upon IP, and eta M is equal to eta BT upon eta IT. Then fifth one is BSFC is equal to m dot F upon B into P. Now the final cycle is air standard dual cycle. For that cycle the PV diagram is shown here. So Qin is equal to QE plus QP, which is equal to CV into T3 minus T2 plus CP into T4 minus T3, and QR is equal to T5 minus T1 into CV. So efficiency is equal to 1 minus QR by Qin. Then compression ratio is R is equal to V1 by V2, and pressure ratio RP is equal to V3 by V2. Then cutoff ratio RC is equal to V4 by V3, and expansion ratio RE is equal to V5 by V4 is equal to V1 by V4. So R is equal to R by RC, then T2 is equal to T1 into R raised to gamma minus 1, and T2 by T1 is equal to R raised to gamma minus 1. T4 is equal to T1 into R raised to gamma minus 1 into RP, then T5 is equal to T1 into RP into RC raised to gamma. Then the final equation for the air standard dual cycle, the equation of efficiency is equal to 1 minus RP into RC raised to gamma minus 1 upon R raised to gamma minus 1 into RP minus 1 plus gamma into RP into RC minus RP. So these are the 12 cycles for the thermodynamic. In general, in this chart we have basically considered just the PV diagrams and the main important equation for the cycles, because if you want to refer all the equation at the one time, you can make this chart in your own way. So if you think that this video is helpful to your other friends also who is preparing for the GATE examination 2021, please share this video as much as possible to them also, and do like and subscribe to the BS Academy. The next video, or we can say the next chart of the thermodynamics, will be coming soon as early as possible. For that video, do subscribe and press the bell icon to get the notification. Thank you so much.